The unfused S and C switch on the unswitched side of the loop is not considered a tap conductor. According to the National Electrical Code Section 240.101b, overcurrent protection is not required for tap conductors that are protected by the overcurrent device of the feeder they are tapped from. However, in this case, the switch is considered a feeder since it supplies power to the transformer. The inspector is citing National Electrical Code Section 230-220, which requires overcurrent protection for all conductors that carry over 100 amps, except tap conductors. Since the S and C switch is a feeder that carries more than 100 amps, the inspector argues that it requires overcurrent protection. National Electrical Code Section 240.101b specifically exempts tap conductors that are protected by the feeder overcurrent device. The unfused S and C switch is not a tap conductor but a feeder. The transformer is protected by a primary fuse in the cabinet. Ultimately, the resolution of this issue will depend on the specific code interpretations of your local authority having jurisdiction. It could be argued that the transformer is protected by the feeder overcurrent device, which are the fuses on both ends of the loop, and that National Electrical Code Section 240.101b applies. The inspector could argue that the S and C switch is a feeder and that National Electrical Code Section 230-220 requires overcurrent protection at that point. Here are some recommendations. Firstly, review the specific code interpretations of your authority having jurisdiction. Secondly, consider installing a fuse or circuit breaker at the S and C switch to satisfy the inspector's concerns. Thirdly, consult with a qualified electrical engineer to discuss alternative solutions. To elaborate further, let's delve deeper into the intricacies of overcurrent protection in this specific scenario. Understanding the precise definitions and applications of terms like feeder and tap conductor is crucial for a correct interpretation of the National Electrical Code. A feeder, in essence, is a circuit that originates at the source of power, such as a substation or service entrance, and extends to one or more branch circuits. It serves as the main artery for distributing electrical power. A tap conductor, on the other hand, is a conductor that branches off from a feeder to supply power to a specific load or piece of equipment. It's a smaller conductor that's connected to a larger feeder. The National Electrical Code provides specific rules and guidelines for tap conductors, including requirements for overcurrent protection. The primary concern behind these rules is to ensure that the tap conductor is adequately protected against overcurrents such as short circuits or overloads that could damage the conductor itself or the equipment it supplies. National Electrical Code Section 240.21 details the requirements for overcurrent protection of tap conductors in various situations. These requirements are based on factors such as the length of the tap conductor, its ampacity, and the overcurrent protection provided at the point where the tap conductor originates. The inspector's interpretation of National Electrical Code Section 230-220 is also important to consider. This section of the code generally requires overcurrent protection for conductors carrying over 100 amps. The inspector's argument is that the S and C switch, acting as a feeder, carries more than 100 amps and therefore requires overcurrent protection at that point. However, the key point of contention is whether the S and C switch should be considered a feeder or a tap conductor in this specific situation. If it's considered a tap conductor, then National Electrical Code Section 240.101b might apply, which exempts tap conductors from overcurrent protection if they're protected by the feeder overcurrent device. To further clarify this issue, it's essential to examine the specific characteristics of the electrical system in question. This includes the size and ampacity of the conductors, the rating of the overcurrent devices protecting the feeder, and the load served by the transformer. A thorough analysis of these factors can help determine whether the S and C switch meets the definition of a feeder or a tap conductor under the National Electrical Code. Furthermore, it's important to consult with the local authority having jurisdiction to understand their specific interpretation of the code in this particular situation. Local amendments or interpretations can sometimes differ from the general requirements of the National Electrical Code. Seeking guidance from the authority having jurisdiction can help ensure compliance with all applicable regulations. In addition to the code requirements, it's also important to consider the safety and reliability of the electrical system. Installing overcurrent protection at the S and C switch, even if not strictly required by the code, could provide an additional layer of protection against overcurrents. This could help prevent damage to the equipment and reduce the risk of electrical hazards. Consulting with a qualified electrical engineer can help determine the most appropriate overcurrent protection scheme for the specific application. The engineer can assess the risks and benefits of different protection options and recommend a solution that meets both the code requirements and the safety needs of the system. Furthermore, consider a scenario where you have a motor control center, often abbreviated as MCC, feeding several motors. Each motor will have its own overcurrent protection device located in the MCC. The MCC itself will be fed from a feeder, and this feeder will also have overcurrent protection. In this scenario, the overcurrent protection for the motors is located at the MCC, not at the individual motors themselves. This is a common practice, and it's generally accepted by electrical inspectors as long as the overcurrent protection at the MCC is sized appropriately to protect the feeder conductors and the motors. Another example could involve a large industrial facility with multiple distribution panels. Each distribution panel will be fed from a feeder, and these feeders will have overcurrent protection located at the main switchboard. The distribution panels themselves may or may not have overcurrent protection, depending on the specific design of the system. In this case, the overcurrent protection for the branch circuits originating from the distribution panels is provided by the overcurrent devices at the main switchboard. This is another common practice, and it's also generally accepted by electrical inspectors as long as the overcurrent protection at the main switchboard is sized appropriately to protect the feeder conductors and the branch circuits. In the case of the S and C switch feeding the transformer, a similar argument can be made. The transformer is protected by a primary fuse in the cabinet, and the feeder conductors are protected by the overcurrent devices at the source of the feeder. Therefore, it could be argued that additional overcurrent protection at the S and C switch is not necessary. However, it's important to note that the authority having jurisdiction has the final say in this matter. If the inspector is not satisfied with the existing overcurrent protection scheme, they may require additional protection to be installed. In such cases, it's often best to work with the inspector to find a solution that meets both the code requirements and the inspector's concerns. This may involve installing a fuse or circuit breaker at the S and C switch, as suggested in the recommendations. It's also important to document all of the overcurrent protection devices in the system, including their location, size, and type. This documentation can be helpful in demonstrating to the inspector that the system is adequately protected. In addition to the National Electrical Code, it's also important to be aware of any local codes or regulations that may apply. Some jurisdictions have their own unique requirements for overcurrent protection. It's always best to check with the local authority having jurisdiction to ensure compliance with all applicable codes and regulations. Ultimately, the goal is to ensure that the electrical system is safe and reliable. This requires careful consideration of the code requirements, the specific characteristics of the system, and the concerns of the authority having jurisdiction. By working together, it's possible to find a solution that meets all of these requirements and provides adequate protection against overcurrents. The concept of series ratings also plays a crucial role in overcurrent protection. Series ratings refer to the ability of downstream overcurrent protection devices, such as circuit breakers or fuses, to safely interrupt fault currents when coordinated with upstream overcurrent protection devices. In other words, a series-rated system ensures that the downstream device will trip and clear a fault before the upstream device is damaged or trips unnecessarily. The National Electrical Code permits the use of series-rated systems under certain conditions, as outlined in Section 240.86. These conditions typically involve specific testing and listing requirements to verify the coordination between the upstream and downstream devices. When applying series ratings, it's essential to carefully select the overcurrent protection devices and ensure that they are properly coordinated. This often requires consulting with the manufacturer of the devices and performing detailed calculations to determine the available fault current at each point in the system. Improperly coordinated series-rated systems can lead to nuisance tripping, equipment damage, or even a failure to interrupt fault current safely. In the context of the S and C switch and the transformer, the concept of series ratings could be relevant if the primary fuse in the transformer cabinet is coordinated with the overcurrent protection devices on the feeder supplying the S and C switch. If the fuse and the feeder devices are properly series rated, then the fuse should be able to clear a fault on the transformer primary without causing the feeder devices to trip. This could potentially eliminate the need for additional overcurrent protection at the S and C switch. However, it's important to verify that the series rating is valid for the specific devices and fault current levels in the system. This may require obtaining documentation from the manufacturers of the devices and performing calculations to confirm the coordination. Another factor to consider is the presence of any sensitive electronic equipment that could be affected by voltage sags or transients caused by fault currents. Voltage sags are temporary reductions in voltage that occur when a fault current flows through the system impedance. These sags can disrupt the operation of sensitive equipment such as computers, programmable logic controllers, and variable frequency drives. In some cases, it may be necessary to install surge protection devices or uninterruptible power supplies to mitigate the effects of voltage sags. Surge protection devices, often called SPD, are designed to divert surge currents away from sensitive equipment. These devices are typically installed at the service entrance, distribution panels, and individual equipment locations. Uninterruptible power supplies, or UPSs, provide a backup power source that can maintain a constant voltage supply during voltage sags or power outages. These systems are commonly used to protect critical equipment that cannot tolerate any interruption in power. In the case of the S and C switch in the transformer, it may be necessary to evaluate the potential for voltage sags and transients and to install appropriate protection measures if needed. This could involve installing SPD at the transformer primary or secondary, or providing UPS for sensitive equipment connected to the transformer. The specific protection measures will depend on the sensitivity of the equipment and the magnitude of the expected voltage sags. Furthermore, it's crucial to consider the long-term maintenance and reliability of the overcurrent protection system. Overcurrent protection devices, such as circuit breakers and fuses, should be periodically inspected and tested to ensure that they are functioning properly. Circuit breakers should be exercised regularly to prevent them from becoming stiff or corroded. Fuses should be visually inspected for signs of damage or deterioration. It's also important to keep accurate records of all overcurrent protection devices, including their location, size, type, and maintenance history. These records can be helpful in troubleshooting problems and ensuring that the system is properly maintained. In addition to routine maintenance, it's also important to have a plan in place for responding to overcurrent events. This plan should include procedures for identifying the cause of the overcurrent, isolating the faulted equipment, and restoring power to the unaffected areas. It's also important to train personnel on the proper procedures for responding to overcurrent events. Effective overcurrent protection is an essential aspect of electrical safety. By carefully considering the code requirements, the specific characteristics of the system, and the potential hazards, it's possible to design and maintain an overcurrent protection system that provides reliable protection against electrical faults.